Hi and welcome. I'm Said Mohammad Hussein Musavi. This course is designed at an intermediate level. So if you're already familiar with the basics of optimization, you can perhaps skip this section. Otherwise, you are in the right place to understand why optimization matters, what it truly means, and how we use it to determine the best course of action in a complex real-world problems. Hi and welcome. I'm Sayed Mohammad Hossein Musavi, and this section covers basics of optimization. We're gonna talk about basics of optimization slightly. So if you are already familiar with the basics of optimization, you can skip this section. This is our outline. So basically, we're gonna cover why optimization, definitions and importance, main types, algorithms, optimization test functions. Why optimization? Because optimization are everywhere. So basically our daily life is covered with the applications of optimization. Optimization algorithms are used every day from AI assistants to delivery apps, and their main goal is to find the best solution under specific constraints. They are the engine of smart decision making in many systems. So they are the foundation of intelligent systems. They help you build smarter, faster, and more efficient solutions. They power everyday tech from Spotify to Google to Tesla. They have application in AI machine learning, navigation and routing, healthcare optimizing, finance, game development, marketing and business, and way more. In the table, you can see some of the application in AI. Signal denoising, regression, feature selection, clustering, image segmentation, resource allocation, parameter estimation, evolve antenna design, space-time wrapping, protein structure prediction, and way more. So basically, optimization is the process of finding the best solution or outcome from a set of possible solutions while satisfying a given constraint. Constraints are the limits or conditions that the solution must meet, like time, cost, or resources. It involves maximizing or minimizing a specific objective function, such as cost or fitness. So when we say fitness, we are talking about maximizing. When we say cost, we are talking about minimizing. An objective function is a mathematical expression that defines the goal of optimization. It evaluates the quality of a solution that guides the search for the optimal result. For example, consider the following equation in red. We are looking for minimizing the fx function x to the power of 2. So basically, we are going to minimize this. The minimum of best solution happens at x equal with 0. Potential solutions in optimization problem are called critical points. Critical points happens when the gradient of an objective function is 0 or undefined. That means there is no slope and the function flatten out at these points. Imagine a hill. At the top of the hill, the slope is 0. This is maximum, local maxima, and global maximum. At the bottom of the valley, the slope is 0. This is minimum, local minima, and global minimum. In between, which is not maximum or minimum, is called undefined. This is called also saddle point. As you can see in the 2D and the 3D figure, the position of local maxima, local minima, global minimum, global maximum, and saddle point is clear. So here are some more definitions about critical points in details. So convergence is so important because all optimization algorithm finally converge to a solution. Convergence is a process of an algorithm that gradually approaching a solution, ideally the optimal one. It means that changing the objective value or parameters become very small over iteration, reaching stability. For example, in the figure, we can see a convergence curve of PSO algorithm on egg holder function. Egg holder function is a test function, which I'm going to cover it in the next slides. As you can see, it is a cost function, so basically it is decreasing. So we have local minimum and global minimum. As you can see, local minimum is a good answer. It is decreased enough, but it is not the best. The best is the global minimum. And that red line shows that the algorithm is converged at this point, and it's not gonna be better over time. However, if we increase the iteration, it might be better, but it is not guaranteed. Anyways, global minimum here is a very good answer, or let's say a very optimized answer or solution. So in the optimization, we have exploration and exploitation. Exploration is a primary phase where the algorithms search broadly across the solution space to identify promising regions or solutions. It helps discover areas that might contain the global optimum. Exploitation is the secondary phase where the algorithm focuses on redefining or improving solution within those promising regions. So basically, it is a search inside the search. So here we can see some definition and applications of the optimization algorithm. You can read it. So we have different types of optimization algorithms. I choose 5 category of them, 5 the most used category of them. For example, gradient-based optimization, which relies on derivatives to iteratively find optima, suitable for smooth and differentiable problems. For example, gradient descent, stochastic gradient descent, or Newton method. Also, we have gradient-free optimization, which operates without gradient information, ideal for non-differentiable or noisy problems, like the Nelder method, a Powell method, and pattern search. Also, we have Bayesian optimization, which uses probabilistic models to optimize expansive black box functions, like Gaussian process optimization or tree structure pattern estimation or TPE. Also, heuristics, problem-specific approach using simple rules to provide quick, often suboptimal solutions like greedy algorithm, hill climbing, and beam search. But the most important of them all, which we are dealing with them here in this course, is metaheuristics. They are general frameworks for global search, balancing exploration and exploitation, covering diverse problems like evolutionary algorithms, swarm intelligent algorithms, physics-based optimizations, and human-based algorithms. And you can see some of the examples of these algorithms here. In general, in metaheuristics, we search for solutions. But in heuristics, we generate solutions. Metaheuristics, depending on the problem, are a bit more complex in time, but they guarantee some good solutions for us. But it is not just like that for heuristics always. Now we cover the algorithms which we are going to employ in the application section. One of them is genetic algorithm. Genetic algorithm mimics natural selection to evolve solutions to optimization problem. In the right, you can find a flowchart of genetic algorithm. Also, in the caption, you can find the paper related to it. 2 main operators in the genetic algorithm are crossover and mutation. Here we can see a simple example of genetic algorithms are for candidates. The objective function here is fitness. So basically we are looking for maximizing the value of x. So we have A, B, C, and D. We can see their binary values and also their decimal values. The higher the better. So basically A and C are selected because they are the most fit. They will be considered as parents. Here we are going to swap their values after the second bit. So the child are going to be 1000 and 1101. Their decimal value would be 8 and 13. This was crossover. Now mutation. Mutation is changing a bit. So basically, a bit randomly selected converted from 0 to 1. Now we replace the old population with the new ones. So basically 6 and 5 from the previous candidates are remained as 3 and 4. Also 1 and 2 are the new ones. We keep repeating until the best solution is found. Ideally is 1111, which is the fitness equal with 15. It is considered to be the best solution. Here we can see the flowchart of differential evolution algorithm. It optimizes by evolving candidate solutions based on differences between them. Also in the caption you can find the paper related to differential evolution algorithm. Just like genetic algorithm, it has mutation and crossover. Also we are going to evaluate the fitness. But the difference is here we are more likely work with decimal numbers, not just bits. Here we can see an example of differential evolution algorithm. It's a simple example. We are looking to minimize the fx function, which fx is x to the power of 2. So we have 3 random solutions, 5, 2, minus 3.8, and 2.1. We start with a random one, which is the x1, 5, 2. So we calculate the fitness. It's going to be 27.04. So now we are going to do the mutation and the crossover here. In the yellow, we can see the equation for it. And as you can see, we have a new constant which is called f. F is a constant, you can change it. In the main paper, it is 0.8. So we are going to use the main value. At the end of operators and equation, we have 0.48. So 0.48 is smaller than 5.2. Now, when we put them into the function, we get 27.04 and 0.23. So now 0.23 is smaller than 27. So basically 0.48 would be considered as the new candidate for the next generation. So we are going to do that each time. Each time we are going to consider a random candidate, and we will repeat this till the numbers converge toward the zero. Here we can see the flowchart of PSO algorithm, or particle swarm optimization algorithm, which is from the family of swarm intelligent algorithms. It simulates the social behavior of swarms to explore the solution space. Swarms like fish or birds, which are swimming or flying with each other toward a specific goal. And you can find the paper related to it in the caption. Here we can see an example of particle swarm optimization. Again, the objective function is to minimize the fx, which is x to the power of 2, just like the algorithm. Now we have 3 particles here. We are going to compute the fitness for each of them. Now we have to compute the personal best, or p best, and global best, or g best. So for the p best, we are going to consider same as the starting positions. But for the g best, we are going to consider the smallest fitness, which is at x equal with 2. Now we have to update the velocity and the position. Please consider that p best is the particle's own best solution, but g best is the swarm overall best solution. So for the velocity, as indicated in the paper, we have a constant formula, which you can see in the yellow, which is v nu, velocity new value, and we have a lot of constants in it, like w, c1, c2, and r1, which are inertia, self-confidence, swarm confidence, and random values. So for each of the particles, we are going to consider and calculate the velocity. For the first one, we have minus 1.5. For the second one, we have 2.5. And for the third particle, we have 0. Now, position, that means the changing the position of the particle. So basically, each particle has to move to with that specific velocity. So for each particle, we will calculate the new position of them, which is 3.1 minus 0.5 and 2. Then we have to evaluate the fitness again. We get 3 new values. We are looking for the smallest value, which is related to the particle number 2, which is 0.25. Now we will update p best. Particle 1 now is 3.5. That means better than before. Also, particle 2 now is minus 0.5. That means better than minus 3. And particle 3 stays at 2, which has no change. So again, we are going to update the g best. As before, we are going to consider the best fitness, which is related to particle number 2, which is 0.25, which was related to the position of this particle, which was minus 0.5. That means particle will now move toward the position of minus 0.5, refining steps by steps until they are all converge near 0. Here we can see the flowchart of firefly algorithm, which mimics the flashing behavior of fireflies using light intensity and attracts other and guide the search for the optimal solutions. Also, you can find the paper in the caption. Firefly algorithm is from the family of swarm intelligent algorithms. So here we can see an example of firefly algorithm. Again, we are looking for the minimum of fx. We have 3 fireflies, which are our candidate solutions, and we are going to evaluate the fitness. So here, lower is better. However, the concept says the brighter is better, but here the function which says minimizing the fx, that means minimizing is better. So there's a main equation which is called attractiveness. That means fireflies attracted to the one which has brighter light, because fireflies are going to produce light. Also, we have 2 constants here, which based on the paper are 1 and 1. So fireflies moves if another firefly is brighter, have the lower fx value. So firefly 1 moves toward firefly 3. Based on the equation, we have 4.9 for firefly 1 now. Firefly 2 moves toward firefly 3 again, because firefly 3 is brighter. So we have minus 3. So basically no change. Firefly 3 has no movement because it is already the best. So we are going to evaluate the new position that are new generation. So we have 24.9, 9, and 4. And this is going to be considered as the new generation. Now we cover optimization test functions. So basically there are a lot of test functions out there. And we're going to test our algorithm or optimization algorithm with these test functions to find out if the algorithm is a good algorithm or not. Is it going to converge for all test functions? Is it going to converge fast enough? So basically, if an algorithm could pass all the test functions available in different types, it is a proper tool to fix a lot of real-world problems using that algorithm. So you can see different definitions about the optimization test functions here. For example, test function in optimization are mathematical functions used to evaluate and compare the performance of optimization algorithm. These functions are carefully designed to represent different kinds of challenges that optimization algorithm might face, such as non-convexity, multimodality, that means it has multiple local optima, or rugged landscapes. They allow researchers to compare the performance of different optimization algorithms on the same problem under specific conditions. They simulate real-world problem complexities to analyze the robustness and adaptability of optimization technique. They're generally categorized into the categories of unimodal and multimodal, but in different shapes. Now, unimodals, which has a single global optimum and is used to test the convergence of speed accuracy of an algorithm, such as A-sphere or Rosenbrock functions. Multimodals, which has multiple local optima and at least one global optimum, and is used to test an algorithm ability to escape local optima and find the global optimum, such as Ackley or Rasterger function. And you can find a helpful link about all of these functions in the caption below. So I just considered two functions from each category to show it to you, but there are a lot out there, so I just considered 8 of them to show it. So from unimodal convex or quadratic, which are simple bold shape with only one minimum, we can go with a sphere function or de-Young function. It is a simple quadratic function. It is a basic benchmark for testing an algorithm. It is very famous. So basically, you can use it for convergence speed. So we have Matthias. It's a symmetric bold-shape function. It's very similar to the sphere used to test optimization method in a smooth low-dimensional landscapes. For the unimodal, I chose Rosenbrock and Powell. Now Powell is multimodal, so basically you can represent it, but what you can see in the figure is a 3D model of it, so basically it is somehow it's modified. Just to show it, some part of it to you. So Rosenbrock is a well-known function. It is a benchmark function from unimodal, but not convex. So we have called them narrow valleys. A well-known function with a narrow valleys leading to the global minimum. It tests an algorithm convergence efficiency. Powell is a complex function with a flat regions. Tests an algorithm performance in scenarios where gradients are small. Here we have multimodal functions. We have many local minima periodic. So basically a lot of real-world problems are going to be multimodal, like what you see here. So RAS region is one of the best multimodal function out there. It contains many regularly spaced local minima. It is widely used to test optimization algorithms in a high-dimensional space. Ackley, which is the most famous optimization test function out there, it features many local minima but one global minimum. It's used to test algorithm ability to converge to the global minimum in a noisy multimodal landscape. So also from highly irregular complex landscapes, I consider just 2 of them, Eggholder and Bale, because they were so famous and also so hard to solve. So Eggholder is the most regular shaped one which I could find. It is a highly non-convex multimodal function used to test algorithms' exploitation capabilities. Bale, a smooth function with a single global minimum, it evaluates the algorithm performance in smooth nonlinear spaces. So here you can see Firefly algorithm on RAS region function. In the right, you can see RAS region function in a 2D shape, and in the left, you can see the performance of Firefly algorithm on it. So as you can see, in each generation, Fireflies try to fit the shape of the RAS region function. Also here we can see some of the other functions, plus the functions which I mentioned here, but they are not all. So basically for more, please find the link in the caption below.